Hi everyone. The next topic is other distributions. So we discussed the binomial distribution and the chi-square distribution in this video. So remember that for each distribution that we have the 4 R functions. For example, for normal distribution, we have the D norm function, P norm function, Q norm function, and R norm function. So this is density, this is probability function, quantile function, and random numbers. So we have already done normal. So we do binomial at first. Okay, so this is binomial random variables. So remember that the binomial random variable represents the number of success. Out of pre-specified the number of observations out of n trials. And each trial so all trials are independent, and each trial has the success probability, and success probability are the same for all trials. So we say success probability as P. So basically we have two numbers, N and P. In normal distribution, we have mean and standard deviation, but for binomial random variable, we have N and P. And if the N and P are given, that we can use this binomial distribution. So here N is called size in R function, and P is called probability, PROB. So here the size is 100 and the probability is 70%, 0.7. So each trial have, each observation, if we generate random numbers, each observation comes from 100 trials with 70% success rate. So that means on average we get 70. Sometimes we get 65, maybe 74 or 81, those numbers. So this is the same as play 100 chess games each day, and your probability to win each game is 70%, and what are the numbers of wins a day for 8 days? So 60, 72, 79, 75, 68, and so on. So how about the probability function, the P binomial? So this calculates the probability that number of wins is less than or equal to 65, given this N and P. So on average, we get 70 wins. So less than or equal to 65, they should have small probability. And actually, we get 16.3%. Yeah. And the next example is another example for continuous distribution and a T distribution. So this T distribution is similar to normal distribution, but slight difference. So basically, T distribution is similar to standard normal distribution, but the distribution, the shape is slightly different from normal. So DF4. So this is slightly more heavy-tailed distribution than normal distribution. We discuss it later, but suppose the normal distribution is like this, then T distribution has heavier distribution, so heavy tail. So value is larger for the tail part, but the smaller for the moderate value. So T distribution is like this, and this blue one is normal. So if we think about the threshold 2, the 2 is actually somewhat the upper tail part. So maybe the 2 is around here. So the probability for the upper tail should be larger for the T distribution. So lower tail probability, so this area should be slightly smaller than 95%, we can imagine. And actually, we get the 94%. So now that we go on to the chi-square random variable. So what is chi-square random variable? So chi-square random variable is the sum of independent and identically distributed normal, standard normal random variables x1 to xn. So chi-square distribution with degrees of freedom n is defined by sum of these standard normal, sum of squares of standard normal random variables. X1 to xn are independent standard normal random variables. So this random variable is basically motivated by the variance, the definition of variance. So variance is summation of xi minus x bar square. So this is more complicated than this formula, but basically we take square of something. If xi is normal, then xi is normal and independent, then xi minus x bar is also normal, and take square, then take summation. So it's similar to the variance formula. So chi-square distribution is used to do something with variance. Yeah, so chi-square random variables. So if we want to generate the chi-square random variables with df3 1000 times, we can do it in two ways. The one is just to use the rchisq function, rchisq function. And we specify df, then we can automatically generate the chi-square random variables. So another way is go back to the definition. If chi-square 3, the chi-square 3 distribution is equal to x1 square, x2 square, and x3 square, where x1, x2, x3 are standard normal. So if you generate 3 standard normal random variables, then we can make one chi-square 3 random variable. So this is the demonstration with R language. If we use rchisq function, you can just specify df is equal to 3, and you can generate 1000 random numbers in this way. And another way is to use normal distribution. So x1 is normal, x2 is normal, x3 is normal. We don't connect anything, so these are independent normal, standard normal random numbers. Then we define C2 as the square of this. Actually, x1, x2, x3 are 1000 dimensional vectors. So for each component, we think about the square, then take summation. So C2 is also the 1000 dimensional vector. So C1 and C2 should be very similar. So in terms of distribution. Just check the mean and the standard deviation for both. And you can see these are similar. Actually, on average, these chi-square 3 random variable should have mean 3. And actually 2.94 and 2.83. So both are close to 3 and close each other. And also the standard deviation. So standard deviation is 2.48 and the 2.34. Actually, the square of this should be equal to 6. So actually, if we take square of 2.48, almost 6, 2.34, almost 6, maybe 5 point something. And these are similar. If we think about the histogram, since we want to see distributions, histogram of C1 and C2 becomes this. So you can see both distributions, these distributions are very similar. Okay, so this is a demonstration for the chi-square random variable. So in this video, we studied several distributions, the binomial distribution that is discrete, and also the t distribution and the chi-square distribution.